Hello there everybody, welcome to a video on section 7.5. Before we dive into it, let me just apologize if you hear my son screaming in the background, throwing a fit in the background. It is because about 10 minutes ago I told him that he had to wear pants, and he didn't take it well. And we've all been there. You know, you don't want to wear pants, somebody tells you have to, so you throw a 10 to 45 minute tantrum over it. We are still early in the quarantine, so I still have minimal standards of like wearing pants around the house. We'll see how I feel in like a week or so. I may have backed off of my must-wear pants parental stance that I've adopted. Anyway, so sorry if you hear a kid screaming. So in this section, we'll return to differential equations. This is day 1 of section 7.5. There'll be a second video on section 7.5 talking about visuals, but we are back to solving systems. Okay, so the goal of section 7.5 is this. We spent some time talking about linear algebra, and I told you at the time we were going to use it to solve systems of DEs. So now is that time. We're going to use things like matrix multiplication, more specifically, eigenvalues and eigenvectors to solve systems of DEs. Okay, so here's a motivating example. We're going to focus on solving systems, linear systems of this form. Derivative of x, vector x, equals a times vector x, where a is an n by n matrix. Notice that if n equals 1, in other words, a is a 1 by 1 matrix, then there aren't really any matrices anywhere. Okay, so I can remove my bolding from the x, and then big A just becomes 1 by 1 number a. So in the 1 by 1 case, you're just looking at this differential equation, a single differential equation. The derivative of function x is basically function x. So again, it's a little confusing here because x is actually not the independent variable. X depends on time here. But what you're saying, right, is that I'm looking for a function whose derivative is basically itself, but with a constant attached to it. And the solution of that is this exponential function here. This guy here, its derivative is basically itself, except you pick up an a. Okay, so all that being said, in the 1 by 1 case, there's not much to say. The solutions are exponential. Now let's consider a 2 by 2 case. This is an example we looked at previously. x1 prime is x1 plus x2. x2 prime is 4x1 plus x2. How would you solve this? Well, at the very least, if exponentials are the name of the game here, you know, in the 1 by 1 case that was true, then maybe the solutions to this are also exponentials. So it seems reasonable to hope that a solution to this system has this form. x1 equals some constant times e to the rt, x2 equals some other constant perhaps times e to the rt. That seems like a reasonable guess for the kind of solutions we should get here. This guess here, this x1 comma x2 is more compactly written like this. x1, x2, the vector, bold x, okay? And what is bold x that we're hoping to be? Constant times e to the rt, and then bottom coordinate, another constant times e to the rt. So we're hoping we can find a solution that looks like this right here. Okay, so again, the matrix notation just makes things more streamlined. Instead of having to write x1 equals this, comma, x2 equals this, right? We're just going to write it in this matrix form, knowing that the top coordinate is x1 and the bottom coordinate is x2. We'll hope that works out for us. Well, in order for that to work, I have to be able to substitute this bold x vector here into the matrix equation here, this differential equation here. You got to substitute it in and get something true. Okay, well, if I do that, if I take the derivative of bold x, well, this v vector is just a constant, so really I'm just differentiating this exponential, and we know how to do that. The chain rule just pops an r down, so I pop an r down, right? On the other side, I'm just plugging in the vector x right there, a times x, where again, x is this v e to the rt. So here I have the derivative of x, of vector x, equals a times vector x. I've just substituted in. So we need that to work out for us in order for this bold x to work. Well, e to the rt, you can divide both sides by that, and then you quickly get this, that r times bold vector v has to equal a times bold vector v. Now, if we were in class, I would look at you and look deep into your souls and ask you, what is this? This equation should look familiar to you, okay? Should look familiar from the linear algebra material. What is this saying about the vector v and this number r? Let me just say in English what this equation is saying. It's saying that whatever vector v this is, right? When you feed vector v into a, you do a times v, you get a multiple of v, right? You get r times v back. So what does a do to v? It just scales it. It stretches it or shrinks it or whatever, right? But the output here is parallel to the input. So all I'm saying is that in order for this kind of solution to work out, this kind of function here, this kind of guess to work out for us as a solution, this bold vector v must be an eigenvector. And this number r, this coefficient on the t up here, must be an eigenvalue. And that's why we spent some time doing linear algebra. In order for this bold x to be a solution, r must be an eigenvalue of a, and v must be a corresponding eigenvector. That's what you would need for this kind of vector to work out, for this kind of solution here to actually be a solution. Okay, so let me just now give you the punchline of this section. Solving a system of d's like this, derivative of vector x equals a times vector x, boils down to finding eigenvalues and eigenvectors. And here's the main theorem of section 7.5. If A is an n by n matrix, so let A be an n by n matrix if A has n eigenvalues that are all real and are all distinct. With these corresponding eigenvectors, the solution to the system looks like this. Constant 1, and here's my first eigenvector, e to its eigenvalue, t. Constant, second eigenvector, e to the second eigenvalue, t, and so on. Notice really quickly the parallel to chapter 3, right? When we were solving not systems of d's, but higher order d's, like second order d's, and then in chapter 4, third and fourth order, and so on. This is what solutions looked like. We just didn't have these bold vectors here because we weren't talking about systems. But we had constant times exponential, plus constant times maybe another exponential, and so on. So you're going to notice a lot of parallels between what we do in chapter 7 and what we did in chapters 3 and 4, and that's very nice. Okay, so here, let's just solve this from scratch. You want to solve this system here. The first thing you got to do is write it as a matrix equation like this, so you have a matrix there, right? Then you scurry off to Wolfram Alpha to ask for eigenvalues and eigenvectors. Okay, so let me just show you how that goes. Scurry off to Wolfram. So in the eigenvalue eigenvector video, I didn't actually calculate them for you. That's something we're going to have to put aside for the course now. If you want eigenvalues and eigenvectors of a given matrix, let me just remind myself what the matrix is. Okay, so 1, 1, 4, 1. You type this, eigenvalues. And then the way you hand Wolfram a matrix is like this. Each row of the matrix, 1, 1, there's a row. So you separate entries by commas, and you delineate the row with curly braces. Sorry, let me zoom in on this. Like that. Okay, so there's my first row. Then comma, that tells Wolfram you're moving on to your next row. 4, 1. Close brace, close brace. So these outer braces just tell Wolfram you're dealing with a matrix. And then inside, each row looks like this, separated by a comma. So if you wanted to add another row, which we don't have here, right? But it'd be like that or whatever. Okay, so now I just hit enter. And Wolfram does what Wolfram does, you know, like it just tells you everything you want to know. There are two eigenvalues, 3 and -1, and then it says corresponding eigenvectors. Wolfram writes its vectors horizontally. We need them vertically, but it doesn't matter. So 1 and then 2, -1, 2. 1, 2 corresponds to 3, -1, 2 corresponds to -1. Okay, so this is what you'll do to get eigenvalues and eigenvectors from Wolfram. You give it a matrix like this, and the command is eigenvalues. So anyway, back here on the slide, that's why I can just like say so quickly. Corresponding eigenvectors and vectors are these to these eigenvalues here. Thus, the general solution is this. Constant, first eigenvector, e to its eigenvalue, t, plus constant, second eigenvector, e to its eigenvalue, t, and you're done. Okay, that's how you solve these systems. Now you may be expected to translate from the vector notation or the matrix notation back to just normal regular notation. So let me just show you how that goes. This is just a more compact way of writing two separate solutions, because vector x, right, has a top coordinate and a bottom coordinate. Its top coordinate is x1, its bottom coordinate is x2. So to get x1, x1 is the top coordinate of vector x. So just read across the top coordinates of this. C1 times 1 times e to the 3t, right? All that. C1, 1, e to the 3t, that all could be put here with that 1. And then what about right here with the negative 1? E to the negative t and c2. So when you read across the top here, that's what x1 is. So c1 times 1 e to the 3t plus c2 times negative 1 times e to the negative t. That's how I get this x1. What about x2? x2 is the bottom coordinate of this vector. So read across the bottom. 2c1 e to the 3t plus 2c2 e to the negative t. So if you have to separate out the two solutions, the two separate solutions, you do it like that. You just take the matrix guy and read across the top, then read across the bottom. If these vectors here had length 3, you could like read across the top, read across the middle, read across the bottom, and so on. So speaking of where you might have 3 by 3, here's an exercise. Solve this system. I want your solution in terms of matrices and also without matrices. So present your solution in this sort of way and also in this sort of way. Okay, so pause the video and see if you can do that. Okay, assuming you're back, here's the solution. So I just went to Wolfram and I asked for the eigenvalues of this matrix. And the eigenvalues I got, I guess, were 6.57, negative 4.57, and negative 2. And these were the corresponding vectors. So just to confirm that, let me scurry off to Wolfram now. Sorry, let me put that there. Okay, so now I got to hand it negative 1, 3, 0. That's a row. 3, 5, 2. That's a row. 0, 2, negative 4. Another row. Boom. Wolfram does what it does. I mean, if you want to keep the answers like this, you can. I approximated them, so you hit this approximate forms button. 6.56, negative 4.57, and negative 2. Those were the numbers. And same thing for the eigenvectors. You don't have to write it like that. If you don't want to, you can just grab the approximate form and shave off to 2 decimal places or whatever. So that's how I got this solution here. And then, again, if you want to write without matrices, x1, just read across the top row. C1, 2.09, 6.57t, and so on. x2 would be reading through the middle. 5.28 C1, this e, plus negative 0.28 C2, this exponential, and so on. Okay, so let me close this video by talking about initial value problems. So this guy here is a system of DEs with no initial value. But now I'm saying, oh, by the way, at time 0, I insist this vector take on this value, 3, 1. So in terms of a system here, if you want to write it without matrices, we've already solved this system here, right? We've already solved that. And we got these two functions here. x1 must be this, x2 must be this. We know that already. Having an initial value on the problem now, what does that mean? That means just what I said, that when time is 0, x1, the top coordinate, must be 3, and x2, the bottom coordinate, must be 1. Okay, so just to zoom out for a second, anytime, in any context, you're asked to solve an initial value problem, it's always the same in the sense that you solve the DE, or the system of DEs, first. So here is that solution where I've ignored this initial value. Then I have to come back at the end and say, oh yeah, they restricted my solutions like this. This is a restriction on the solutions, right? When time is 0, I have to have those values. So let me just put the consequence of that. When time is 0, x1 is supposed to be 3. So here's a 3, and then if you plug in time 0 in here, right, you're just killing these exponentials to 1. So c1 minus c2. When time is 0, x2 is supposed to be 1. So there's a 1. And here's x2. If you plug in zeros for t, you get 2c1 plus 2c2. Right? This is a 2 by 2 regular algebraic system. You can ask Wolfram to solve that for you if you want. And the solution is c1 is c4 and c2 is actually negative 5/4. So that's why there's a... Oh, sorry, I said that wrong. C1 is 7/4, and C2 is 5/4. Yes. If you ask Wolfram to solve this for you. So I just slot C1 in there, C2 in there, and now right here I got to put a twice C1, and here I got to put a twice C2. So that's how I get a 7/2 and a 5/2 with a negative on it. Okay, so at the end of this video, you should be able to solve systems of DEs where the eigenvalues are all real and distinct. Okay, oh, sorry, just real quick. This guy here, you could compactify it like this if you wanted to. You know, this problem didn't ask you to, but here's the vector form of the solution. 7/4 e to the 3t, 5/4 e to the negative 3t, right? If you read across the top row, that's what you would get. Anyway, so if your matrix has real, distinct eigenvalues, we know what to do. If you think back to chapter 3 with the characteristic equation, if that had all real, distinct roots, we knew what to do. So back in chapter 3, we then said, oh, but you might not get all real, distinct roots. You might get like complex roots. What do you do about that? The next section, 7.6, is about that. The next video, though, is not section 7.6 yet. The next video is talking about visualizing these systems with slope fields. But anyway, where we're going next is what do you do when the eigenvalues that Wolfram spits out to you are complex, or maybe they're repeated, you know, maybe they're not distinct. So that's where we're headed.